All right. Hi, everyone. Welcome to the recording of the 10.3 notes over ideal gas law. In today's lesson, you will be able to use this ideal gas law to solve for an unknown variable. And when I'm talking about an unknown variable, I'm kind of talking about when we had pressure, volume, number of moles, and then temperature of a gas. So these are kind of variables that we were talking about. The other thing that we're going to do in this lesson is we are going to apply the stoichiometric relationship between moles and volume. So there's going to be a relationship there that we'll be able to see. What we already know here is that pressure, volume, and temperature can vary for an amount of fixed gas. Stoichiometry or dimensional analysis is the relationship with the matter in a chemical reaction. It's how we convert from like moles to grams, moles to moles, things like that. And don't forget that the coefficient in a balanced chemical equation represents the mole ratios that we have. Now let's go ahead and skip this next part. We talked about that next lesson, or last lesson. So here's the ideal gas law equation. Before we were talking about our gas laws where we had a before and after for a single sample of gas. We talked about conditions where, oh, what if we only looked at pressure and volume? What if we only looked at pressure and temperature? What if we looked at volume and temperature? Here we have a sample where there's not going to be a before and after. There's just like a current time with the gas. So these variables in this equation, we've seen a lot of them before, but the only thing that's different is that every single variable should be used using the a very consistent, very same unit. So P stands for pressure, of course, and the pressure unit that we should be using is atmospheres. So make sure that you use ATMs for pressure. For volume, V, make sure that you're using L for liters. Temperature, we're going to do the same restriction as before. We're saying that temperature must be measured in Kelvin. We didn't talk about R too much last time, but this is called the ideal gas law constant. And as long as we're using atmospheres and liters and Kelvin, and we'll see moles as well, the value of R will always be 0.0821. And the units here are liter atmospheres per mole Kelvin. You don't have to worry about that too much. As long as you're using your numbers correctly, the units will not, shouldn't get in your way, but that's the official units for the ideal gas law constant. So let's look at an example of solving a problem using the ideal gas law equation. Something else I want to say is a lot of times when people are talking about this PV equals nRT, they might also say is P times V is equal to N times R times T. And most simply, they'll just call it Pivnert. They'll call it the Pivnert equation, just because that's when you're trying to say it, that's what it sounds like. Let's look at this example problem together and kind of see how we solve this. As long as you kind of know what units you're supposed to use and what the equation looks like, and you have some basic algebra skills, these should be pretty straightforward to solve. We are going to use this PV equals nRT equation. So let's go ahead and populate that with all of our variables, what they're supposed to be. Did I already read this? So a 5-gram sample of oxygen has a pressure of 198 kilopascals when stored in a container with a volume of 148 milliliters. What is the temperature of the oxygen gas? Okay, so we're given 4 of these unknown variables, and we're being asked for the other one that we don't have. So let's go ahead and list out what we do have. P is 198 kilopascals. Are we allowed to use kilopascals here? The answer is no. We need to convert this to atmospheres. So in every 1 atmosphere, how many kilopascals were there? There should be 101.3 kilopascals. So if we do this math, 198 divided by 101.3, the amount of atmospheres that we actually have in this equation is 1.95 atmospheres, which we are allowed to use in our math here. Our volume is given to us in milliliters. We have 148 milliliters. However, according to this ideal gas law equation, we're supposed to be using liters. So in every 1 liter, how many milliliters are there? 1,000. So we should have 1,000 milliliters in there. I mean, that's what a mil means. So 148 divided by 1,000 gets us 0.148 liters, which is what we're allowed to use in our equation. Okay, N. Do we have moles of oxygen? The question does not give us moles of oxygen, but we can calculate it from the information given. So before we calculate this, what is the chemical formula for pure oxygen? It should be O2. So that's important here because it does influence how we solve this. So the amount that we're given is 5.0 grams of O2. So if we're trying to convert this to moles, so for every 1 mole of O2, what should I put at the bottom there? So a single O2 is 16 grams per mole. Since it's 2 of them, we're going to double that and make that 32 grams of O2 for every 1 mole of O2. We're getting these numbers from the periodic table. These are the molar masses. So 5 divided by 32 gets us 0.16 or so moles of O2. And this is what we're allowed to use in our equation here. So this question has been kind of annoying. It's making us set up everything with a lot of work first. But once we set up everything, it should be pretty straightforward. The value of R. The value of R is always going to be the same, y'all. It should be 0.0821. And then liter atmosphere per mole Kelvin. The main thing here is the number. Can we get the number correct? Make sure you put 0.0821 and not 0.821. That's a very common mistake I see students make. Finally, the temperature. We have no idea what that is. We're going to solve for that with the ideal gas law equation. So this ideal gas law equation will allow us to be able to basically calculate the temperature of this gas without ever using a thermometer. So let's go ahead and plug in all these numbers into my ideal gas law equation and use algebra to solve for my unknown temperature. So pressure is 1.95 atmospheres. Volume is 0.148 liters. Let's see. It looks like number of moles is 0.16 moles. R is 0.0821 liter atmosphere per mole Kelvin. And I don't know the temperature, so I'm going to leave it as T. So we're going to solve for this unknown T, just like you'd solve for an unknown X in algebra, using our algebra skills. So if you're comfortable doing this all in one step, go ahead and do that. Like, for example, I would do 1.9 times 0.148 divided by 0.16 divided by 0.0821. That would solve it right away. But if you're not comfortable doing that, just do it step by step. So let's solve the left side first and then solve the right side as much as we can. 1.95 times 0.148 gets us 0.289 or so on the left side. On the right side, this 0.16 times the 0.0821 gets us 0.013 or so times our temperature. So how do we solve for our temperature now? We want to get it by itself, so we have to divide both sides by what it's currently being multiplied by. So let's divide both sides by this 0.013 to get temperature all by itself. And on the right side, that just cancels out. But on the left side, we do actually have to plug that into our calculator. So 0.289 divided by 0.013 gets us 22 or so. So my units of temperature from this, what are those units supposed to be? This should be given in Kelvin because all of my calculations should spit out temperature in Kelvin for these gas law equations. So that's how we solve something with the ideal gas law equation, y'all. The main thing you have to look out for is, am I given the units that I'm allowed to use first? Like if I don't have liters, how do I get to liters? If I don't have atmospheres, how do I get to atmospheres? If I don't have moles, how do I get to moles? That's what this question forces you to do. The other thing you might have to look for here is like if they give you degrees Celsius, make sure you convert that to Kelvin first as well. All right, next question here. A sample of nitrogen gas has a pressure of 8.7 atmospheres, a temperature of 48 degrees Celsius, and a volume of 2.8 liters. How many atoms of nitrogen are present in the sample? Okay, weird question. They're asking for atoms of nitrogen at the end. But to me, I'm thinking that's probably related to moles in some way. So I'm just going to solve for moles and figure out what it's asking me later. So I'm going to list out my variables again. Pressure, volume, number of moles, gas constant, and then temperature. Pressure is given 8.7 atmospheres. Volume is given in 2.8 liters. I don't have to convert either of those because that's what I wanted already. I don't know my number of moles of nitrogen gas. And then my gas law constant should be the same number. That's what we call it, a constant, because it's constantly the same. So 0.0821. And then our temperature is 48 degrees Celsius, but we're not allowed to use that in our equation. So we do have to add 273 to it to get Kelvin. So we actually are dealing with 321 Kelvin as our temperature here. Questions so far? All right. So I can just plug this stuff into my equation again. You don't have to rewrite the equation if you don't want to, but I'm just showing what I'm doing. So for P, I can plug in 8.7. For V, I can plug in 2.8. For N, I don't know what that is, so I'll just keep it as N for now. For R, we of course have 0.0821. And then for T, I do have 321. All right, so I can start, computing this. I can start calculating and solving for N. So on the left side, I can do 8.7 times 2.8. Gets us 24 or so. On the right side, I can do 0.0821 times 321. And I get N times 26.4 or so. So I do want to get N all by itself. Since it's currently being multiplied by 26.4, I want to divide both sides by this 26.4 to get N all by itself. And I get, let's see, the right side cancels. The left side I have to calculate. So 24 divided by 26.4 gets me something like 0.91 moles of this nitrogen gas. Okay, so I'm closer to solving this problem. I'm really close. Now, nitrogen gas, what's the formula for nitrogen? Is it N or is it N2? So it is part of Brinkelhoff. That means it is N2. So pure nitrogen is a diatomic element. It is N2. So I want to be really, really clear on some terminology here, y'all. An N atom is if we have a single N like this, okay? An N molecule, an N2 molecule. An N2, we call it a molecule because there's two atoms that are bonded together. So an N2 molecule might look like two N's like slightly overlapping, all right? So in every single N2 molecule, how many N atoms are there? There's two of them, exactly. So we're going to take that into account when we're answering this question. So I'm going to start off with this. I'm going to do one final conversion here. I'm going to do 0.91 moles of N2. I'm going to try to get individual units here. I'm going to try to get to molecules of N2. So for every 1 mole of N2, how many molecules are there of N2? Yes? Not 5. There are 6.02 times 10 to the power of 23 molecules in every 1 mole of N2. A molecule is a type of particle here. Yeah. So then we just said that, we're being asked for atoms. We're not being asked for molecules here. And in every single N2, in every single 1 molecule of N2, there's going to be 2 atoms of N2. So we do have to multiply by 2 at the end, basically. Okay, so that's the basic setup here. Moles cancel out. Molecules cancel out. We are left with atoms. So I can do 0.91 times 6.02 E23 times 2, and I get about 1.1 times 10 to the power of 24 atoms of N. I need to relabel this a little bit as my final answer. And that's all using the ideal gas law equation and some stoichiometry or dimensional analysis. Stoichiometry is just using dimensional analysis. Questions so far, y'all? Yes? No? No. I thought it was like a pick on me, but it was actually a finger wag. No way. No questions here. Finger wag. All right. Let's do maybe one more example problem. I think we can skip the last one because I think you're getting the idea. But let's look at one more really quick. Before we do that, I want to give you one useful fact. So whenever we're talking about N, as we saw that already, that's the number of moles of gas produced. But something else about moles of gas is that at STP, and STP is standard temperature and pressure. And that means that you have 1 atmosphere of pressure and 0 degrees Celsius of temperature. That's what that means. At STP, you might see questions like this that will use this relationship. 1 mole of any gas whatsoever. It could be methane gas. It could be oxygen. It could be nitrogen. 1 mole of any gas would equal or take up 22.4 liters of space. So if any gas, we're saying basically in this class, is at 1 atmosphere pressure and it's a chilly 0 degrees Celsius, then it will take up 22.4 liters of space. So if I ask you a question that's like something like, oh, at STP, how many liters does 3 mole of methane gas take up? Then you would simply be able to do, okay, 3 moles times, 1 mole over 22.4 liters, do 3 times 22.4. And then you would get the answer at something like 67.2 liters of gas is the volume of that gas. That's an example type of question you might see. Now, let's say you forget this number. You're like, oh, I didn't know 1 mole is equal to 22.4 liters. As long as you remember that standard temperature and pressure is 0 degrees Celsius and 1 atmosphere, then you should be able to plug this into your ideal gas law equation and still get it, okay? It's just the ideal gas law equation, it's a lot of work for like just a simple relationship here. Okay, last question. When zinc is placed in HCl, a single replacement reaction occurs and produces hydrogen gas and zinc chloride. And we do have this balanced chemical equation below that shows this. A sample of 5 grams of zinc is placed in a beaker with excess hydrochloric acid, the HCl, and allowed to completely react. The hydrogen gas is collected and has a pressure of 825 millimeters of mercury and a temperature of 55 degrees Celsius. What is the volume of the hydrogen gas? All right, so this is looking like a PivNert question to me. So I'm going to define my variables. I'm going to list out what they are and then figure out how to solve this problem. So my pressure, it says, was 825 millimeters of mercury. I think I'm only allowed to use atmospheres. So I'm going to convert this to atmospheres real quick. For every 1 atmosphere, I know there's supposed to be 760 millimeters of mercury. So 825 divided by 760 gets me like 1.09 atmospheres of gas. For volume of this hydrogen gas, it looks like I'm being asked for that. So I don't know that quite yet. It's a mystery. I'm going to solve for that later. For number of moles of hydrogen gas, okay, this is where you're supposed to like really think about it. Maybe use your stoichiometry skills with chemical reactions. We're only given that there's 5 grams of zinc, 5 grams of Zn. So we need to somehow get from 5 grams of Zn to moles of hydrogen gas. That means that you need to start converting this to moles. 5 grams of Zn has a molar mass of 65.38 or so grams of Zn for every 1 mole of Zn. And then we can convert this to moles of hydrogen gas by looking at our chemical equation. We see that for every 1 mole of Zn, there's 1 mole of H2. So for every 1 mole of Zn, there's 1 mole of H2. I can go ahead and calculate this. Grams cancels out, moles cancels out. 5 divided by 65.38, we get like 0.08 or so moles of hydrogen gas, which is what we're looking at here. Questions so far? All right. My gas law constant should be 0.0821, just like before. And then my temperature is given as 55 degrees Celsius, but I really should change that to Kelvin by adding 273, which gets me 328 Kelvin. Okay, we have all our numbers. Let's go ahead and plug it into our equation. Our pressure is 1.09 atmospheres. Our volume is unknown. Our moles of gas is 0.08 moles. Constant is 0.0821. And our temperature is 328. So I can basically solve for V by dividing both sides by 1.09. And my final volume, I can plug that into my calculator all at once. 0.08 times 0.0821 times 328 divided by 1.09. Gets you about 2. 2 what? Two liters, exactly. And that would be my final answer of this problem. Just like 2 liters. I ran it to 1 digit there. We weren't expected to be too precise for this one. All right, do you all feel like you need to do another example? Or do you feel like you're getting the idea? All right. There is one more example here. If you want to try it out yourself and then look at the key for that, you may do that. I do think it's very similar to the last problem in terms of how you start solving it. I will go ahead and end this recording here. Thanks for watching. Hopefully this helps somebody.